How to troubleshoot dangling pointers and prevent memory leaks. Imagine working on a program that suddenly crashes or starts behaving strangely. It might be caused by tricky issues like dangling pointers or memory leaks. These problems can be sneaky and hard to spot, but understanding how they happen is the first step to fixing them. Let's explore how to troubleshoot dangling pointers and keep your program running smoothly. Dangling pointers happen when a pointer still points to a memory location that has already been freed or deallocated. If you try to use that pointer, it can cause crashes or data corruption. Common causes include freeing memory without resetting the pointer, returning pointers to local variables that go out of scope, or using uninitialized pointers that point to random memory. To identify these issues, watch for symptoms like segmentation faults, unexpected data, or compiler warnings about returning addresses of local variables. Using debugging tools is a smart move. Tools like Valgrind or AddressSanitizer can detect invalid memory accesses and show you where dangling pointers or leaks occur. Static analyzers can also scan your code for potential problems before you even run your program. Regular code reviews and thorough testing, especially on edge cases where objects are destroyed or memory is freed, help catch issues early. To prevent dangling pointers, always set pointers to null immediately after freeing memory. This way, if you accidentally try to use a null pointer, your program will crash quickly, making the mistake obvious. Never return addresses of local variables from functions because they go out of scope once the function ends. Instead, use smart pointers if your language supports them. In C++, smart pointers like unique pointers or shared pointers automatically manage object lifetimes, reducing manual errors. In languages like Java or C#, relying on garbage collection to handle object cleanup. Adopting defensive programming techniques also helps. For example, you can implement a tombstone method where you associate a small marker with allocated memory to indicate if it is still valid. Before accessing memory, check this marker. Another approach is using locks and keys, where pointers carry a key that must match the memory's lock, preventing access to stale pointers. Always match each memory allocation with a corresponding deallocation. Avoid freeing the same pointer multiple times, which can cause undefined behavior. Using resource management patterns like resource acquisition is initialization ties resource lifetimes to object lifetimes, making cleanup more predictable. Regularly, run memory profiling and leak detection tools during development to catch issues early. By following these steps, you can catch dangling pointers before they cause trouble and prevent memory leaks from sneaking into your code. This keeps your program stable, secure, and efficient. Mastering these debugging and prevention techniques is essential, especially in low-level languages like C and C++, where manual memory management is part of the process.